So we're going to talk about the confidence interval for the mean response and the prediction interval for a new single observation in multiple linear regression. So the outset is that we have some data here, data points, and in our example, the x1 regressor, that's the pH value at which the chemical process has been conducted. And there's a temperature as well. That's the x2 value, the x2 variable. And we measure the yield for each time we run the process, and that gives us these data points. And we've made a linear fit. Maybe it looks something like that. It's a plane that best approaches these data points. And we've used the method of least squares to establish this plane here. It has an equation which is beta naught plus beta 1 times x1 plus beta 2 times x2. And we remind ourselves that beta 1 is the slope with respect to the x1 dimension here. And beta 2 is the slope. It's hard to draw here in 3 dimensions, but beta 2 is the slope in the x2 direction. Beta naught here, that's the intercept with the y-axis, the intercept of the plane with the y-axis. So we'd like to use our model to make predictions. Of course, that's why we make it. So maybe we would like to know, let's say we choose a pH value of 2.3 and a temperature of 38 degrees. What is our model's prediction for the yield at those variable values? Well, the most probable yield according to our model, that's whatever this number is here. So we get that number by finding the projection of our point here on the plane and reading off on the y-axis the value. That corresponds to inserting our point here, 2.3 plus beta 2 times 38. And that gives us the value. And if I remember correctly, beta 1 is minus 1.68. Beta 2 is 0.13, and this is 59.05, doing the regression from the example from the previous videos. So we can use this to compute this number here, which is then this value here. But we'd like to do better than that. We'd like to find a confidence interval, because we know that, and I'll use the green color for this, we know that if we did this regression, or again with a new set of data points, we'd get a slightly different plane due to random variation, and if we did it a third time, we'd get a different plane again. So this plane is not it's not perfectly determined. It's a result of a random sampling process. So yes, this is our best guess. This thing here is our best guess for yield, but we know that there is some random variation going on, so that it would be more interesting to do like a 95, perhaps 95% confidence interval for this yield here, because we know that this number is probably not what we're going to find if we did the experiment again. So acknowledging that this plane is not the absolute truth, we do a 95% confidence interval of that mean response that we would expect according to the model. So that's to say that if the plane looked slightly different, we did the experiment again, we might get a slightly different plane do that yellow here. Maybe the plane would look something like, oh, that wasn't a plane at all. Something like this. And the intercept would then be here, maybe. And then if we did it again, it might look something like that, and we'd get an intercept here. But 95 of the times, the intercept from this point here with the plane would be in this interval here. That's kind of what we're computing here. And then we're interested in finding what's the model prediction for a new observation, a single new observation. That's what we call the prediction interval for a single new observation. And that's even more uncertain, because not only do we have to take into account that these planes can vary somewhat due to random variation, but also, even though the plane has been fixed, let's say we knew the plane was here, where the black plane is, there would be variation around that plane. The single observations are not all placed on the plane, they would be scattered above and below the plane. So there's the uncertainty of the plane's position itself, and then there's the uncertainty of the single observations around the plane. So that gives a wider, you could say more uncertain, less precise prediction interval. We talked about that earlier. The way we compute the prediction interval and the confidence interval is I mean, the general idea is the same. We have the most probable outcome, that's this y value here, so that's just beta naught plus beta 1 times x1 plus beta 2 times x2. So that's the most probable outcome, and then we have to add and subtract some variation, and that's going to be a t quantile according to the what confidence level we want to compute it at. That's alpha, and it has n minus k minus 1 degrees of freedom, where k is the number of regressors in our model. In our case, that's 2. And we have to multiply it by the standard error of the mean of the response given some set of regressive variables. This x h here is a vector. I'll get back to it, but it's a vector that contains the number 1, and then 2.3, which is our choice of pH, and 38, which is our choice of temperature. So it contains the coordinates of the regressor variables that we're interested in. Yeah, and for the prediction interval, we have the same most probable yield, which is computed in the same way. x1 here is 2.3, and x2 is 38. Again, same thing up here. 2.3, 38. And we add and subtract the t quantile with the same number of degrees of freedom and multiply by the standard error of the single of the prediction of the single observation here. So the question now is, how do we compute those standard errors? And that's what we're going to look into here. In order to make any sense out of the formulas, we need to define a few things here. We have to define what we call a design matrix. That's a matrix which contains ones in the first column, and then the x1 variable, let's call it x11, x12, x1, 3, and so on down to x1, n. Let's say we have n data points in our regression here. And the next column is then, that's the second, so that's the temperature. This is the pH. And then we have the temperature column, x1, no, sorry, x2, but it's the first of the observations. x2, 2, x2, 3, and so on, down to x2, n. So this is the dimensions of this matrix is, see if I can write it somewhere else. The dimensions is k plus 1, because we have 2 regressors and then another column here. And the number of rows is n, so corresponding to how many data points do we have in our in our data material. Now it turns out that the variance of the mean predicted response, so this is the square root. This is what we're looking for, but that's just the square root of the variance of the mean predicted response. So the variance of the mean predicted response is given by this formula, which I won't derive here, but it's the total variance of the y values times the xh vector, that's this one here, multiplied by the design matrix transposed, multiplied by itself, and then everything inverted, multiplied by the xh vector transposed. So that gives you the variance of this mean. So that's basically the variance of the green curve here. The variance, and if you want the standard error, which we do, we'll just take the square root of this number here. The variance of the predicted single observation given some regressor variable values here is almost the same, but there's just another contribution of the variance here. So we get sigma squared plus, and then the same thing as before, completely the same thing, like that. So there's another term, there's another contribution of variance, and that's just what I talked about before. So this represents the uncertainty, this thing here represents the uncertainty of the plane itself. And then once we've established that, so to speak, then we have another contribution of uncertainty, which is the individual observations scattered up above and below the plane. So that gives us the variance of the predicted single observation. And we take the square root of that, and then we have this quantity here that we want for the prediction interval. So these two formulas are important, and we have not derived them. We won't derive them. Maybe I'll link to a video that derives them if you're interested in that. I don't expect you to be able to explain these formulas, but I expect you to be able to use them. And we'll try to use them in Excel in the next video.